10.1 Angular Position, Velocity, and Acceleration. The outline of this video is as follows. We will begin by introducing the rigid object model and how it simplifies our analysis of motion. Next, we will define the three primary rotational quantities: angular position, angular speed, and angular acceleration. Finally, we will examine the vector nature of these rotational variables. We start with an introduction to rotational kinematics. Our approach here is parallel to the way we analyzed translational motion in previous chapters, but now we apply it to rotation. We utilize the rigid object model, which assumes that the object under study is non-deformable. This means that the relative locations of all particles that make up the object remain constant during motion. A key feature of this model is that every individual particle on the rotating rigid object moves in a circular path around a fixed axis of rotation. Let us define angular position, which we denote with the Greek letter theta. We can describe the position of any particle p on the object using polar coordinates, r and theta. Because we are dealing with a rigid object, the distance r from the center remains constant for any specific particles. The angular position theta is defined as the angle between a reference line fixed on the object and a fixed reference line in space, such as the x-axis. Mathematically, theta is the ratio of the arc length s to the radius r, d. This definition allows us to calculate the arc length s as er times theta. This slide presents figure 10.1, which depicts a Blu-ray disc rotating about a fixed axis. The axis passes perpendicularly through the center point, O. We focus on a single particle p located at a fixed distance r from the origin. As the disc rotates, this particle moves along a circular path, sweeping out an arc length s. The angle theta represents the angular position of the particle relative to the fixed reference line. We must now discuss the units used for these angles. Although theta is defined as a ratio of lengths and is technically a dimensionless number, we assign it the unit radian. 1 radian is physically defined as the angle subtended when the arc length is exactly equal to the radius. Since the circumference of a circle is 2 pi times r, a full 360-degree rotation corresponds to 2 pi radians. It is vital to avoid a common pitfall. In all rotational physics equations, you must strictly use angles expressed in radians, never degrees. This slide illustrates the concept of angular displacement. As the rigid object rotates, the particle moves from an initial angular position, theta initial, to a final angular position, theta final. We define the angular displacement, delta theta, as the final position minus the initial position. This quantity describes the net angle through which the object has rotated and is directly analogous to translational displacement, delta x, in linear motion. We can quantify how fast an object rotates by defining its angular speed, denoted by the Greek letter omega. The average angular speed is the ratio of the angular displacement to the time interval delta, t. The instantaneous angular speed is the limit of this ratio as the time interval approaches 0, which is equivalent to the time derivative of the ktos. The units for angular speed are radians per second. By convention, we define omega as positive for counterclockwise rotation and negative for clockwise rotation. When the angular speed of an object changes, we say it has an angular acceleration, denoted by the Greek letter alpha. We define the average angular acceleration as the change in angular speed divided by the time interval. The instantaneous angular acceleration is the limit as time approaches 0, or the derivative of omega with respect to time. The units are radians per second squared. It is important to note that alpha is positive if a counterclockwise rotation is speeding up, or if a clockwise rotation is slowing down. We must also understand that rotational quantities behave as vectors. For rotation about a fixed axis, the angular velocity and angular acceleration vectors point along the axis of rotation itself. We determine the specific direction of the angular velocity vector using the right-hand rule. If you curl the fingers of your right hand in the direction the object is rotating, your extended thumb points in the direction of the vector omega. The angular acceleration vector alpha is parallel to omega if the rotation speed is increasing, and antiparallel if the speed is decreasing. Let us summarize the key points of this section. Rotational kinematics describes motion using variables that are strictly analogous to translational motion. Angular position theta corresponds to linear position x. Angular speed omega corresponds to linear velocity v, and angular acceleration alpha corresponds to linear acceleration a. The standard unit for these measurements is the radian. Finally, remember that for a rigid object, every particle shares the same angular position, speed, and acceleration. We conclude with 2 review questions to test our understanding. First, consider a wheel where the angular position changes from -1 radian to +1 radian in 1 second. To find the average angular speed, we calculate the total displacement, which is 1 minus -1, resulting in 2 radians. Dividing by the time of 1 second gives us an average speed of 2 radians per second. Second, consider a top spinning counterclockwise that is slowing down. Counterclockwise motion means the angular velocity omega is positive. However, because it is slowing down, the acceleration must oppose the motion, meaning the angular acceleration alpha is negative.